Hello students, I am Dr. Krupa Rasane, Professor and Head ENC, Jain College of Engineering, Belgavi. We'll be continuing with the Module 5. This is the first video of the Module 5 in Power Electronics, BE 7th Semester, ENC BTU. Module 5 basically consists of pulse width modulated inverters, and we have about 10 hours for it allotted. And in that, we can divide it into two parts. First one is the pulse width modulated inverters themselves, which consists of these particular topics, that is introduction, principle of operation, performance parameters, etc. And we have one more topic that is included in this particular module, and that is static switches, in which case we'll be dealing with some AC switches, DC switches, and solid state relays with microelectronic relays as well. The textbook that we are referring for this particular module is again the textbook 1, Mohammad Rashid, Power Electronic Circuit Devices and Applications. So basically it consists of DC to AC converters. In this particular video, we'll be dealing with at least 4 subtopics. That is, we'll introduce you to inverters. What are the performance parameters? We'll be also looking into the principle of operation, and also briefly look into single phase bridge inverters, specifically with the half bridge inverter. The other topics will be covered in the forthcoming video. So coming to the introduction, basically DC to AC converters are known as inverters. Means input is DC and output is AC, which we normally have at our homes. When the power goes, we have a battery supply, and which is connected to these inverters, which will give you AC, which are connected to the some of the loads like fan, television, etc., so that we get uninterrupted power supply. The function of an inverter is to change a DC input voltage to a symmetric AC output voltage of desired magnitude and frequency. So the output is AC, input is DC, and the output magnitude could be whatever you desire, fixed, and also required frequency as well. So the output voltage could be fixed or variable at a fixed or variable frequency. Both output voltage and frequency can change. A variable output voltage can be obtained by varying the input DC voltage and maintain the gain of the inverter constant. So increase the input, right? Output is equal to gain times the input. So either you increase the input and keep the gain constant, or you keep the input voltage fixed and change the gain. Okay, so there are different ways to get the output. On the other hand, if the DC input voltage is fixed and it is not controllable, a variable output voltage can be obtained by controlling the gain of the inverter, and such type is called as the pulse width modulation or PWM control within the inverter. So this is the most popular inverter to get the output voltage. So the inverter gain may be defined as the ratio of the AC output voltage to the DC output voltage. We are familiar with the gain term. Continuing with the introduction, now the output voltage waveforms of any ideal inverter, we require it to be a sinusoidal. But in practical inverters, they are non-sinusoidal and also contain certain harmonics. Normally, if a waveform is not sinusoidal, it means it does have certain harmonics with it. So for low and medium power applications, we can even deal with square wave or quasi square wave voltages. It is acceptable. But when we come for high power application, low distorted sine and sinusoidal waveforms are required. So with the availability of high-speed power semiconductor devices, the harmonic content of the output voltage can be minimized or reduced significantly by the switching techniques. So when I'm going to use the pulse width modulation, it is going to deal with switching technique, and it is possible to minimize these harmonic contents that come at the output so that the load is operating at a better AC output. Inverters are widely used in industrial applications. Example would be variable speed AC motor drives, renewable energy, transportation, induction heating, standby power supplies, and uninterrupted power supply. The input may be a battery, a fuel cell, a solar cell, or other DC source. So input has to be DC. So these are some of the different ways that we can have an input. So battery, fuel cell, solar cell, or any other DC source. Now the typical output voltage that are commercially available for an inverter are 120 volts and 60 hertz, 220 volts at 50 hertz, and 115 volts at 400 hertz. So depending upon which country you are, where the applicable required voltages and how the loads are basically operating, we can either select any of these required output voltage. So the inverters again can be classified basically into two types, single phase or three phase inverters, and each of these can be controlled with the turn on and turn off devices such as BJT. You have MOSFETs, we have IGBTs, we have MCTs and SITs and GTOs. So all of these devices we have studied in our initial chapters, the chapter 1. And now we'll be basically looking into these particular devices being used in inverters as a switch. These inverters generally use PWM control signals for producing an AC voltage. So an inverter basically could be called by different names. One is the voltage fed inverter. So when you look at the voltage fed inverter, we also call it as VFI if the input voltage is said to be constant. If the input current is maintained constant, then we call it as current fed inverter or CFI. And there's one more inverter called as variable DC linked inverter where the input voltage is controllable. It is not fixed. So basically we are dealing with these types of PWM controlled inverters. Either it could be single phase or three phase, or it could be controlled using a constant input voltage, in which case we call it as voltage fed inverter. If constant input current is maintained, then we have a current fed inverter. But if the input is controllable, then we call it as variable DC linked inverter. There is one more. If the output voltage or current of the inverter is forced to pass through zero by creating an LC resonant circuit, this type of inverter is called as resonant pulse inverter, and it has wide applications in power electronics. So this is another type of inverter. So these are the different types of inverters that we have been looking into. Next is the performance parameters. The input voltage to an inverter, you can see this block diagram. So input is basically DC and the output is going to be AC. So the output normally is obtained in this format, right? And it looks like a square wave. Of course, they're not looking like a sinusoidal, but we can convert it into sinusoidal or semi-sinusoidal using some filtering elements like capacitors and inductors. And because this is the load, right? This is the load voltage, and load current will flow only when I connect a load to it, right? And what we observe is the input current, that input current is load current is supplied by the input current, but the waveform of the input current is distorted. Okay, so you can see it rises initially during the on time, then it becomes off, and hence there are two levels of current here, right? Lower level and peak level, and the center of that we call it as the average value. Okay, so just looking at these points, the input voltage in an inverter is DC and the output voltage is AC. The output should ideally be AC or pure wave, but the output voltage in a practical inverter consists of a square wave and hence has harmonics or ripples. The inverter draws current from the DC input source only when the inverter is connected to a load, and the input current, as we can see, is not a pure DC, but it also contains harmonics as shown in this particular figure C. So now let us look at the performance parameters. The quality of an inverter is normally evaluated in terms of the following parameters. So what are performance parameters? It is by knowing these values that I will come to know how good an inverter is, what quality of waveforms I get at the output. So let us look at how to, which are these parameters and what the values of these parameters tell me about the quality of the output of the inverter. So the parameters are go like this. First one is the output power, which is given by PAC, which is equal to I naught V naught into cos theta. And this can be summed up as I naught squared into R, where both V naught and I naught are the RMS load voltage and load current. And theta is the angle of the load impedance and R is the load resistance. The AC input power of the inverter is, we know, is IS into VS, input voltage into input current, where Vs and Is are the average or DC input voltage and input current. Then what is the RMS value? The RMS ripple content of the input. So obviously, as we have seen in the previous slide, the input current is going to rise from one level to another level. So we'll have a ripple. So how do we get that? Is ripple current is got it as square of I1 squared minus Is squared, where I1 and Is are the RMS. This is RMS and this is the average supply voltage of the DC supply current. Okay, and the ripple factor can be got as ripple factor of the input is got as equal to IR upon IS, where IR is root of I1 squared minus IS squared upon IS. So these are a few of the performance parameters. Let us look into other performance parameters. So here we have looked into the input AC input power. We have looked into the output power. We have looked into the input ripple content and we have looked into the ripple factor of the supply input current. Continuing with the performance parameters, the power efficiency, which is the ratio of the output power to the input power, will depend on the switching losses, right? Which in turn depends on the switching frequency of the inverter. So harmonic factor of the nth harmonic. So the harmonic factor of the nth harmonic, which is a measure of the individual harmonic contribution, is defined as, we have done even in rectifiers, controlled rectifiers, what is harmonic factor and what do we mean by the nth harmonic factor. So harmonic factor or the nth harmonic factor can be got as V on upon V0n, nth harmonic output voltage upon the fundamental component V01 for all harmonics greater than 1, where V01 is the RMS value of the fundamental component and V0n is the RMS value of the nth harmonic component. So this is the harmonic factor. And then we have one more term called as the THD, that is the total harmonic distortion, which is basically a measure of how close the shape is to the how close in shape between a waveform and its fundamental component is defined. So total harmonic distortion is given by 1 upon V01 into, under the root sign, summation of n harmonics from 2 onwards to infinity, all the harmonics are included, a square term of V0n. So this is the total harmonic distortion term. So another performance parameter that we are looking into. Next is the distortion factor, that is DF. So THD, which gives the total harmonic content, it does not indicate the level of each harmonic component. Okay. If a filter is used at the output of the inverter, the higher order harmonics would be attenuated more effectively. Therefore, a knowledge of both the frequency and magnitude of each harmonic is important. So as I said, if I want a good waveform at the output, I have to connect a filter. And now he says that if the filter is required, I should know the magnitude of these harmonics and also the frequency of the harmonic. The DF, that is distortion factor, it indicates the amount of HD that remains in a particular waveform after the harmonic, that is harmonics of that waveform have been subjected to a second order attenuation that is divided by N2. So this distortion factor, it indicates the amount of harmonic distortion, and how do we evaluate it is we subject it to a second order attenuation or second order filter, which is basically divided by N by 2. Sorry, N2. So thus distortion factor is a measure of effectiveness in reducing the unwanted harmonics without having to specify the values of second order load filter, and is basically defined as df equal to 1 upon V01. Again, the whole under multiplied by summation of all the harmonics from 2 to infinity, where inside the summation we are doing output of n harmonic upon n squared, the whole square under the root sign. So the df of an individual or nth harmonic component is defined as nth harmonic distortion factor is nothing but equal to V0n upon V01 n squared for all n harmonics greater than 1. So these are the terms that we have to be familiar. And so now let us look into the principle of operation. And in the first case, let us look into single phase half bridge inverter. The circuit diagram for this is we have got a 3-point supplier here. You can see Vs is connected to two parallel capacitors C1 and C2, and the center of these capacitors, the load is connected in this fashion, and these are the two choppers Q1 and Q2, and we have D1 and D2 as the freewheeling diode, which will freewheel whenever your choppers are not conducting, or they carry the load current when the choppers are not conducting. So if you look at the waveform B here, we have got a situation. See now when Q1 is a chopper, when it turns on, let's say from 0 to T0 to by 2. What happens is this point and this point, it's turned on means connected. So this is the load. So what happens? The voltage across C1 is how much? Vs by 2. How did I get Vs by 2? This Vs gets divided between C1 and C2. So I get Vs by 2 with plus minus on top, and Vs by 2 with plus minus on top with C2. Now when Q1 conducts, what happens? This point gets connected here, and the other end of the load point gets connected here. So this load is basically connected to across C1, and we assume that D1 is not conducting now. So C1 comes across the load, and the positive point of the C1 is connected to this terminal, A terminal, and the negative terminal is connected to this particular 0 terminal. Okay. So what happens is, and I have shown the polarity of voltage as plus and minus. So obviously plus is connected to the plus of the load, and negative is connected to the negative of the load. So obviously the voltage across the load, I show it as the voltage across this capacitor, which is nothing but Vs by 2. So from 0 to T0 by 2, I get this particular positive voltage. Now when Q2 is turned on, note when Q2 is turned on, the positive of the load is connected to this end, and the negative of the load is connected to this end of the C2 where plus is connected. So when Q2 turns on, this circuit is closed loop and Q1 is off. And during that state, the plus point comes to the negative terminal of the load, and the negative point comes to the plus point of the load. So the output load voltage is going to reverse for the duration of the T0 by 2 to T0. Getting the point? So if you look at, this is the current that is flowing, that is the current carried by Q1. So I1 is the current flowing, and it is going to flow in this direction. We know transistor carries in one direction only and flows through the load in this direction. Since it is plus, we show positive current that is flowing in this direction. Next is I2. I2 is also going to carry the current in this direction, right? But it is opposite basically for the load. So for the load I'm showing opposite. But since I2 through the Q2 is going to be in this direction only. Okay. So for the load, it will be reversed, but for Q2, you have to show it in this direction itself. Now this is the load current. Now in load current, you can see we have got how many switches here? Q1, Q2, D1 and D2. Q1 and Q2 are basically the choppers and D1 and D2 are the freewheeling diodes, and they carry a current of the load whenever your chopper is off. So D1 will carry the current in this direction and D2 will carry the current in the opposite direction for the load. So when D1 is conducting, current is going to flow in this direction. When Q1 is conducting, current is going to flow in this direction. Are you getting this? Right? So when the Q1 is conducting, I call it as positive. Right? So I get a positive current when Q1 is conducting. And when D1 is conducting, it has to be in this direction. That is reverse of the diode. And hence when D1 conducts, it is negative current. Okay, and similarly with Q2, when Q2 conducts, the current has to be negative, so I get the negative direction. And when D2 conducts, the current will flow in this direction, which is opposite to Q2, so it has to be basically positive. So when D2 conducts, I am going to show the positive, means above 0. So above 0, who all are going to conduct? Q1 and D2. Below 0, Q2 and D1 is going to conduct. So this is how your single phase half bridge inverter works. Continue. So let us relook now at the principle of operation of the single phase half bridge inverter. So we have seen that in figure 1 how the circuit is. We have a 3-point power supply. Two capacitors are connected across the power supply and it consists basically of two choppers Q1 and Q2. And when transistor Q1 is turned on for the time t0/2, the instantaneous voltage across the load would be Vs/2, that is voltage across the capacitor C1. And if Q2 is turned on, then for the time duration, for the next half of the time duration, then the voltage C2 across C2, that is minus Vs/2, will appear across the load. So for some period I get positive voltage, for some period I get negative voltage, and hence I'll be getting an AC at the output. Very simple. So the logic circuit should be designed such that Q1 and Q2 are not turned on at the same time. And figure B shows the waveform of the output voltage and transistor currents with a resistive load. So there we have seen that there is a current phase shift between the output voltage and the input current theta. Now this phase shift occurs if the load is inductive and this value of theta becomes equal to 0 if the load is resistive. So it should be noted that theta 1, the phase shift of the fundamental component of the current, is 0 for resistive load. The inverter requires a 3-wire DC supply, I have told you, and when a transistor is off, its reverse voltage is Vs instead of Vs/2. Okay, but we have a diode which will conduct and hence the voltage across the Q1 also reduces the voltage across the diode. The inverter is also known as half bridge inverter. Okay, so we'll also have a full bridge inverter which will be looked at in the forthcoming videos. So looking at this half bridge inverter, let us look at the performance parameters. So the root mean square or the output voltage can be found from V0, which is the root mean square value, RMS output voltage, is nothing but integration of 0 to t/2. It's a square wave both with positive and negative, and the values will be Vs²/4 because the amplitude is Vs/2. So when I squared it, it becomes Vs²/4 under the root sign. So this is your RMS value. We know the formula. And this becomes equals, if I solve it, this becomes T0/2 and 2/T0 cancels out. And Vs becomes Vs4 becomes 2 because of this root sign. And this becomes the output voltage, which is Vs/2. This is the RMS output voltage. Now, if you look at the instantaneous output voltage, it is going to be nothing but a Fourier series. And I am going to have V0 equal to the DC component A0/2 plus the harmonics consisting of the cos and the sine term with AN and BN. Okay, so this is a DC term and with an and bn are the coefficients of this Fourier series. Now we know that the triangle waveform that we have seen, the area of the positive and the area of the negative is equal to each other and is symmetrical across the x-axis, and hence both the a0 and an terms are going to become 0. A0 is average value, it is going to be 0, and an is the an coefficient in the Fourier series, even that will be 0 because it basically has an its symmetricity across the x-axis. So we'll be getting only the Bn term. You use the same formula that we have done for control rectifiers, and Bn values you will be getting as 2 Vs by n pi. So in that instantaneous output voltage, which I explained in the previous slide, this term will be 0, this term is going to be 0, and we are going to be left with Bn sine n omega t. So Bn, if I substitute 2 Vs by n pi, this term sine omega t, and we will note that this V naught has a value only for the odd terms, and its value becomes 0 for all the even terms because of this sine function, where omega is nothing but 2 pi f naught. F naught is the fundamental frequency. It is the frequency of the output voltage in radians per second. And due to the quarter wave symmetry of the output voltage along the x-axis, the even harmonic voltages are absent. For n equal to 1, if I substitute n equal to 1 in this particular equation, right? This will give me V naught 1 becomes equal to 2 Vs upon root 2 pi. So n is substituted as 1, and we have the sine of omega t. Okay, sine omega t is there. So I take only the RMS value Vs by root 2 upon pi. So that becomes equal to 0.45 into Vs. So dear students, we have been looking into the inverter, DC to DC converters. We have seen the introduction. We have seen the performance parameters. We have also seen the principal operation and with respect to a single phase half bridge inverter. In the next forthcoming video, we'll be looking into the single phase full bridge inverters. So thank you for your patient hearing. If you have any doubts, do get back to me with queries. Thank you so much.